You can just change the mode probably. Yeah. I'm audible here, right? Yeah. Good evening. It's a pleasure for me to be here in this pretty prestigious meeting of yours. I'm sorry, I just came in late and probably just here for the public lecture. I will try to keep it light because it is expected to be for public, but I will try to connect our mission on the sun and also related to this conference in terms of the pattern recognition and so on. I think you got some example from my previous speaker how astronomy is becoming important for pattern recognition and artificial intelligence. So I will try to give you a flavor of what we are doing in the context of solar physics as well. So first of all, I'm just representing the science working group from Aditya Mission. The mission of this class, involves many institutions, thousands of people, and we are just some of us are making this presentation to the public. You see from the series of logos here, these are the institutions which are actively involved with this mission in its science planning, hardware, and eventually data analysis. Very briefly again, since it is a public talk, I will say why sun is important for our daily life and on the context of the physics as well. We do see different states of variability in the sun. Sometimes we see this kind of very dynamic events. This is a image of the sun taken from Solar Dynamic Observatory. This is one of the NASA satellites. It's looking at the higher atmosphere of the sun, namely the corona. This is solar corona, not the virus. Incidentally, the coronavirus was named by looking at the total solar eclipse images. When the biologists looked in the microscope, the virus, it suddenly clicked on their mind that it looks familiar. Actually, the total solar eclipse does show the extended coronal features in the form of those helmets and so on. And that's how the virus was doing. Some should not be blamed for it, but that's the story, actually, connecting. Now, we see that certain portions of the sun, the intensity or the brightness looks to be much stronger as compared to the other regions. And historically, these regions have been called as active. And the other part of the sun has been named as quiet region. But this is a completely misnomer. Now, with the modern observation, we know that nothing is quiet in the sun. Every part of the sun shows certain dynamics. It's only that our observational capabilities have now enabled us to see that dynamics even in the quiet sun. And in fact, the understanding the quiet sun, so-called quiet sun, is very important because these regions are regions where there is a presence of strong magnetic field underneath. They're called sunspots. And these sunspots always come in bipolar form, and they're connected by these huge magnetic structures called coronal loops. And because of the certain stability, the plasma is confined in this. So this is again a cortex supernova of sizes several megameter inside. So you can see why it is so important to study the plasma physics in the astrophysical context and in the sun. So these are some of the dynamics which happens in a shorter time scale, minutes to hours to days. But then there are longer term variations also, which I will talk about today, which affects us in our long term existence here in the earth. The other, since again this is a public talk, I normally try to impress on the youngsters that the solar physics is one of the oldest subjects why they are so important. Because it is an ideal laboratory for plasma physics, atomic physics, nuclear physics, particle physics, and many. I can think give a couple of hours of lecture on each subject and impress on you. And since you heard about this, I had no clue about astronomy before I went to Bangalore. I had a pure theory because physics background. I need for a PhD interview. I was not selected in IAPR department. Was selected in the African game. That's the reality of it. So sometimes I tell these stories to the students to know that sometimes it just happens to come on a way and then it becomes part of your theory. So and I do enjoy whether it was an accident. I think it was the right path. So again, coming back to sun, these regions are called sunspots. They come in bipolar form. These are called magnetogram. That means the maps of locations of the magnetic field on the sun. They are very important now. Data for us to find the magnetic variability of the sun on a daily basis. If I now zoom over any sunspot, you will see there are much more complexity. There are much more dynamics. I'm not going into details of that, but just be aware, and that's the size of Earth. You can see one particular sunspot is as big as the size of the Earth, or even could be bigger. So the amount of plasma which is confined in these active regions are enormous. And when they have become unstable, and you saw this explosion, the material carrying away, makes a big impact in the interplanetary environment. Now, what it plots here is essentially the last 400 years of record of sunspot numbers. Certain days on the sun, you will find two sunspots. Certain days, you will not find any sunspot. It can go as long as within a couple of years that there are no sunspot at all. It happened in our recent past. So what it first depicts is that the sunspot number periodically changes. There is a cyclic behavior. Sometimes some cycles are very strong, and other times the amplitudes are weaker. These periods are typically 11 years, but it's not strictly 11 years. But one thing to be noted, way back in 1650 to 1700, there are hardly any sunspots recorded. Of course, the telescopes were small, and just first 50 years of telescope discovery, 1605 onward, Galileo also worked on sunspots. In fact, he also looked at the sunspot movement and found out that sun is rotating around the same axis. So all these, gives us the impression that this magnetic activity of the sun has a long-term visibility. And during this 50 period, we now know that Europe was extremely cold. Volga was frozen for 40 years. So this is all related to the mini ice age. Now people do go back and look at other properties from cosmogenetic other elements, and it is now known that probably 22 or 23 kind of mini ice ages in last millennium. So that means that's not affordable in the modern era. And of course, it may solve a little bit of global warming problem. But another way of how you can look at it, if sun becomes too active or too magnetically strong, then it will again produce a lot more energy. Incidentally, all the atmospheric models consider sun emission to be constant. That's actually all astronomers also consider. It is called solar constant. But it does vary by 0.01%. So this minor variation of the total solar energy flux we could only measure when we started going to space. Of course, if you measure it in from capita or in anything, you will find different numbers. So that's why it was important to go to space to get an accurate measure of the total energy flux coming from the sun. And what is shown here is, so this is again a UV image of the sun, which depicts again the coronal emission taken from SOHO satellite. Incidentally, it is also at the Lagrange 1 point, launched in 1995, still alive. So what is plotted here, the blue ones depict the total solar flux, and here is the magnetic cycle, the total sunspot number. It perfectly, correlates. Globally, glossally, you are seeing this, but again, there are minute, small little changes. This is also a very important thing. What we now realize is that this is the flux integrated over all wavelengths. But now, if we look at individual spectral window, we will find that the influence will be much more. For example, the UV flux is much more, important for our climate. We know the ozone layer depletions, atmospheric disturbances, and all that also has a lot to do with UV. So near UV flux now be modeled to be very important for our climate. That's why in IAPR, again, I will come back and show you. We have the first, near UV image on that, which will look at these irradiance, the total solar output in near UV. So that's a long-term change. Of course, these are the short-term change. You have seen such huge explosions, and again, for a comparison, I've depicted here the size of the Earth here. So if you now see that these huge plasma material, if it goes into the interplanetary space, what kind of havoc it can do. So what we do is we create artificial eclipses. Incidentally, the emission from the corona, what you are seeing, those images looks bright because they are in UV and so on. But if I now compare the solar disk, intensity and the coronal intensity, they're 1 millionth time less the coronal intensity. So only during the total solar eclipse, if you have not, what's observed in total solar eclipse, probably you will remember, moon perfectly blocks the solar disk, occults the solar disk, we call it, and then you see the corona. But for that, we have to travel across the globe. So in physics, you need coronal observation. So scientists designed a instrument called coronagraph, which artificially blocks the solar disk and looks at the inner corona, and this is an outer corona. And as you see, when this huge ejecta comes out, it does travel in the interplanetary space. And again, I'm sure you will not be very happy to be moving around there. This is again a close-up of CME as recorded by the partner solar probe. This is a new mission from NASA. They are going much closer to the sun. We will be traveling all the way almost to 0.3 AU to as close as to the sun. IAPR, we are only going 1.5 million kilometers, with 1% of the distance. Please, keep that in mind. But what I wanted to highlight is that to basically, understand these new ejecta, their properties, their sizes, their width, is very important because when they travel to the interplanetary space, they are affecting our space assets, and we need to save them. So we need to model them. This is becoming a reality. In '89, there was a complete blackout in North America, in Canada, and the metro also stopped for 4-5 hours. It was extremely cold, climate at that time, March. You can see this, and apparently the insurance company had to pay out some $10 billion. So that's a good amount of money. Now the insurance companies are probably going to fund some of our research in terms of predicting such events. Of course, mitigation is a next problem, but whether you can predict such event to happen or not. Mr. X launched 40 Starlink satellite. Of course, we all know Mr. X is attitude. He never bothered to look at the sun. Or there are warnings incidentally that there could be some solar storms, but they are not of strong nature as well. But it's not the storm itself directly impacted with that. The entire interplanetary medium, it gets affected. So the drag forces, which is imparting on the satellite when it is initial phases of its trajectory, was completely changed. So these satellites never could reach actually 400 kilometers or 500 kilometers, what it was expected to be, and all the 40 satellites were lost. So that's again $1 billion loss, but again, Mr. X can probably afford that. But hopefully next time he will consider taking some prediction and choose the right window for launch. So this is becoming a very, very important exercise to choose. You only hear about near Earth weather, but the space weather is also very, very important for all space assets. The launching is again just one example of like that. Thankfully, Earth has its own magnet. So we are protected because of this cocoon. All these energetic particles and material when it comes, it cannot cross those magnetic field lines, and we are protected. Particularly people like us who are in the low latitude. But these continuous flow of material which comes from the sun in the form of these ejecta, which are transients in nature, but there is also a continuous flow from sun outflow, which is called the solar wind. That is also not a constant. It has a variability with the solar cycle. Depending on how strong the solar magnetic field is, that dictates the interplanetary magnetic field as well. So all the propagation of whether it is material or it is particles is completely dictated by the interplanetary magnetic field structure. And that interplanetary magnetic field can completely get changed if the solar magnetic field is very different, or if you have a very extended minima. So when the sun is very active magnetically, we call it maxima. When it is weaker, we call it solar minima. During the minima period, their interplanetary magnetic field can be very different. And then the transient propagation will be very different as well. So here, you see, if it would have been a simple dipole, it should have been symmetric. This is the sun side. So it is very, very different in the presence of, the solar wind and all this ejecta. But what we can have is, these particles can, come through the polar region. That's what they try, because they come here, they sort of, gyrate along the magnetic field lines. They cannot cross straight away, and they try to enter to the higher latitudes. And that's how, it can give you auroras and so on. Probably I have a picture of that. So these solar storms generate energetic particles and aurora. This is a picture taken from Lagrangian one point by a solar spacecraft. So you see the camera got flooded with these cosmic rays. So it's not a pleasant environment to be. And of course, if you are doing a spacewalk, then you are affected directly by that. Incidentally, all this space tourism is going to be a reality in the near future, particularly for very rich people. So we need to protect them. So we need money upfront from them as well. So this is the beautiful auroras which you see here. And this is, of course, there is a bit of chemistry involved. There are often 5 ions and get charged and so on, and you get this beautiful picture. So this is a reality now to have a new field called space weather. I often give this example when at least I was young. We used to go to the seashore like Puri or nearby area. In the morning, the fisherman will listen to the radio whether it is safe to go to the sea for fishing. So now it will ISRO or other space companies are give us a call whether it is safe to launch the satellite. So that's one example. But there are other companies. Of course, all the communications are heavily dependent on the ionosphere. So ionosphere gets disturbed when there is such transience. You have, I mentioned about astronauts' safety. The galactic cosmic rays, which is coming, also gets deviated because of the nature of the interplanetary magnetic field. In the minimum time and the maximum time, they're very, very different, and that provides an proxy as well. We are very much dependent on of course, on the communications. The GPS. GPS gets heavily affected by these solar storms. And again, in turn, all the drilling, whatever happens, apparently they need very precise GPS coordinates. Even if a few minutes of disturbance causes havoc for them as well. There are long-haul flights. I don't know how many of you are aware that when you take now, it looks pretty or very comfortable. Take a direct flight to New York from Delhi, but it takes a polar route. So it goes through Greenland and so on. Actually, you are getting bombarded by those solar energetic particles. In fact, airline companies should give a statutory warning when such solar storms are likely to happen, because it does, have a good doses, which unfortunately we do not have a real quantitative measure. What is the dose which is acceptable to our human body? Like people say that the X-ray machines in the airport is quite safe. But there are new X-ray machines with this TV and all that. Sometimes it may not be very safe for pregnant women, for example. So similarly, these kind of flights are very, very harmful for pregnant women. So I don't know whether airline companies are really going to have a declaration on these elements. So space weather is a reality, and with all that little background, I will now jump into our mission, Aditya. What is plotted here is again the solar cycle. Just wanted to highlight how much time it takes to deliver such a payload. We started our business way back in 2006, and it was conceptualized for a low Earth orbit with a single payload, a coronagraph, with imaging capability and so on. It was just a 100 kg kind of payload maximum and a small satellite program. It was formally approved by ISRO, and the money was awarded and so on and so forth around 2009. So we were working on it. Almost the components were getting procured and so on. Then around 2013, something just before that happened, we had a successful Mangala mission, and ISRO became very adventurous. So ISRO was not really too keen to go for low Earth orbit missions and all that. It was cakewalk for a lot of the mission. But then Professor Rao, he just called some of us and said, would you like to go somewhere else? I mean, what do you mean by somewhere else? Where? Say, for example, L1. I knew about L1 because I couldn't believe, years that India could reach L1. It's 1.5 million kilometers away. We are only talking about 200. Of course, the operationally were successful because we had around the 10 years before that. But what's said and done, it is the European Space Agency and NASA so far has reached it. China attempted, there is still no record that they were successful. Of course, there is no science mission program, something we can do before our neighbors. So the project was completely modified, and as usually it happens, the scientists were given opportunity and we grabbed it. That, how many payloads we can give. There was an announcement of opportunity, several institutes submitted proposals. 7 payloads were chosen with a full-fledged observatory in space. So it's unbelievable that such a, this is our first solar dedicated mission, and we have a full-fledged observatory. So this is only possible probably in India. ISRO is also ready to take a risk with people like us. We are first-time builder of such instruments. So that's actually a believable, frankly. So it's really, the scientific community should be, engaged ISRO, the opportunities what ISRO is providing to us. Of course, we had the COVID challenge because this is a period over which, all the lab work was happening. We are supposed to get all the component assembly, testing, and labs were closed almost 1.5 years, 2 years. So it got delayed. Eventually, the payloads were delivered in first half of this year. It was not in January, I would say January, February, as our period slowly, one by one, the payloads were delivered. Again, this is unbelievable that integration in the satellite, all the system verifications. There are a huge number of tests, vibration tests, thermal tests. They all did that within 4 5 months. It's unbelievable, and that too when Chandrayaan-3 landing was also going on. So this is only possible in India. I tell you, I'm involved with the NASA mission where the launch is scheduled in 2025. The payload is being delivered next week. So that is the kind of time frame which takes for a space mission. But of course, we took much longer than the ISRO's capabilities. Eventually, we were in space, and on 2nd September, that was the launch. This is a sequence of things which happened. We were lucky to be there inside. Yeah, probably you can identify some of the next to me, and then the other 2 bomb connection. There were thousands of people in the hot weather outside, waiting for the launch. There are several sequences of this. I will not get into the full details of the different phases, but it took almost 1 hour for the L1 separation. And this is the liftoff from what you see, quite a bit of tension at that point. And finally, we had a successful launch. Very briefly about the different Lagrange points. So essentially, there are 5 Lagrange points for a 2-body system. And the 3rd body, if you just take it as a satellite, and you put, in this 3-dimensional space, you will get 5 Lagrange points. So we are L1, which is in the sun-earth line. L2 is a very good location for astronomy, particularly night part of the sky, because the sun is, blocked, and JWST is there. L3 is just behind the sun. Of course, it is quite good for solar observation because we only see one face of the sun. We never can see the backside. But only problem is if you go to L3, you cannot download any data in the current configuration because the sun blocks the telemetry. So we have to be ingenious in some way in future to think about going to L3. L4 and L5 are very good vantage points for solar observation again, but it's again very large distance. Incidentally, Professor Rao was ready to take us to L5 as well. So we are still working on it. You never know. We will be there someday. Okay, so that's the orbit which was taken. Of course, if you would have a bigger rocket or Yeah, this is again another thing. It's always makes optimization, and in some kind of innovation they always bring in. And this is again another example. Most of these launches we are doing it in this pattern. That have a screenshot stuff. 5 orbits, and then around 22nd we left the Earth centered orbit. We are in the cruise phase. We are very close. We are very close. This slowdown is quite something. From Mangalan, if you recall, it was quite tension that you have to get into gravity of Mangal, otherwise you will just miss that. Then we have to bring it back, which is harder. So in fact, on a lighter note again, we just had a workshop. We were thinking about the next mission, space mission. So the name of the workshop was ARIES L1 workshop, and beyond ARIES L1 workshop. So then the last day, somebody asked the question, hey, we are all doing this, but suppose IAPR, is not able to insert in that orbit, what will happen? Then, but then we said we should have a meeting, which is called beyond ARIES, beyond L1. So basically, IAPR will go to beyond L1, then what you can do, the science, so we have to think about. So jokes apart, we are almost there. I will show some data already. Again, this is a fantastic thing. We were not aware that we were supposed to open any doors before the L1 inception. Officially, we are only going there on 7th of January 2025. But in the cruise phase already we have started operating for 2 hours at an instrument. Not all. And thankfully, majority of the instruments have now successfully sent some data. I will show you some of those pre-data. Again, uncalibrated. This is again a sea change in, I think, ISRO's attitude. Because earlier things were very protective, and we also didn't know what's happening. But now I see the first result we see from the tweets of the chairman. And then we are allowed to work on the data and so on. But it's fantastic because it really motivates a lot of people. Common again, this is general public talk. I'm just sharing that sentiment what we have and how excited we are for the data. So this is a particle detector. As it was leaving the Earth's orbit, essentially it has recorded what kind of particle flux, because that time we were inside the magnetic cocoon of the Earth's magnetic field. So as we leave, then there will be sea change, and I'm told by the aspect team they have found already some interesting observations on that. Hopefully it will come. Again, I want to point out that often these Lagrange things and so on. Basically, around the Lagrange one point when we are rotating, it's a halo orbit, but it's not in one plane as well. This is something which you have to realize. Of course, we haven't got the exact simulation from ISRO itself yet, but these are examples from other ESA and NASA missions. I could manage to get the these animation from NASA, and so that's the kind of orbit which it's a huge halo orbit, but not in one plane, and it takes several months to make one orbit. So it's a very slow movement. Essentially, the force between the satellite and the Earth is balanced by the force between the sun and the satellite. Essentially, for any particular thing to be in space, you need to actually have a central orbit. So whatever centripetal force you need in the central orbit is supplied by these two. So you have to solve actually quite a few terms to get into that 5 Lagrange point solution. So you have to keep that in mind. It's not a fixed point. Can I just, I think there is a little bit of audio here.
This emission line studies the superprism and dynamics of Earth's ice ejections. The Solar Ultraviolet Imaging Telescope, SUIC by building, images the solar disk in near ultraviolet and also measures the solar reactions. The Olympic solar wind particle experiment aspects and plasma analyzer package for Olympic Papa studying the solar wind and energy technologies as well as their energy distributor. The solar low energy X-ray spectrometer, so Nexus, and the high energy N1 orbiting X-ray spectrometer, Helios, study the X-ray planets himself through one energy range. The magnetometer is N1 sonic waves within the N1 to develop by different laboratories and and in your considerable master represent certain aspects instrument factors of the laboratory and the body. Space Spirit's laboratory, Vikram's online space center, so Nexus and Helios payload at UR satellite center, Bengaluru, at the magnetic equator, at the laboratory for electro-optics, URSC.
So I must point out that all the payloads are built in different institutions or labs of ISRO. So this is a complete Make in India project. Of course, I must point out that we still do not make chips. We do not make optics. Having said that, it is the only place, the mirror, which we wanted to have a very good polished surface and all that. Each mirror would have costed about 10 crore from an outside source. ISRO decided to build that in their own laboratory. So the new facility was built up within years, and we have now got the best. So this is the best polished mirror India has ever produced, and this is flying in there. So this is just an example. There are many such where built in ISRO's lab because our industry is still not ready to make such predictions. That's unfortunately. But that way, we are, I think, making progress of technology demonstration within the country. So, I think this is a good example of that. And even Chandrayaan had one payload in the US, but all this 10% payload that developed. Oh, sorry. So maybe just very briefly, it's a multi-payload observatory class mission. We are also covering multi-wavelength. This is going from shortest wireless to X-rays to all the way to optical. We are covering here. We don't have radio here. So that's a big payload coronagraph which is sitting in the top. VLC built at IAA, which you heard now. Suit instrument is built in Pune, in Ayuka. So this suit has been opened. I will show you some results of suit. Very, very fresh, hot cake kind of stuff. We have a combination of 4 remote sensing and 3 in-situ instruments. Remote sensing means we are at Lagrange one point, so remotely we are looking at the sun, and we are trying to identify and characterize the properties of the source region of these all these eruptions and whatever happens in the corona and all the dynamics and so on. Whereas in-situ means if something comes from the sun before it reaches Earth, it has passed through the Lagrange one, and then we will detect the properties of those particles of the magnetic cloud or the CMEs, their magnetic field properties, the charge states and the ion states and so on. It's like a thermometer putting in your mouth in situ. So that's called the in situ measurement. So that combination also makes a good observatory class because we have also expertise required people from in situ lab kind of environment and the remote sensing environment. So in situ experiments, very briefly, this are the aspects which I showed those fluxes. It has several components. It has directional properties as well. And the magnetometer is going to actually only spread out after we reach one insertion. It's like a folded arm and then it will open up as we reach there. What we expect, so normally if there is a huge, magnetic cloud, we call it a CME, which comes, it has also different components. There is some core, then there is a void region. These are basically magnetic flux rope, these are magnetic structures of huge size, traveling, and there is a shock in front. So you expect to see these kind of fluctuations in the magnetic field, velocities, the number densities, temperature. GAC is a parameter which actually measures the Earth's magnetic field. So eventually you will have momentary changes in the Earth magnetic field at certain locations where these geotectonic storms will arrive, and the electron densities and so on. But again, if there are different kind of transients coming, here another example we have shown, if there is a stream, we call it co-interactive regions between the fast and the slow solar wind, because the solar wind is also having different velocities at different latitudes. Then you see a different kind of signatures. Why I'm showing this, that these are all ingredients for AI. Because the nature of the fluctuations, the time period of the fluctuations, magnitudes of the fluctuations are all giving you training data set. So in this context, I'm just trying to build, and we'll show a few examples. Yeah. So we just briefly.
Let it run your ourselves. Through even and super class picture. And dynamics and solar atmosphere. Solar with distribution and temperature accident. And initiate new interventions, plans, and new Earth days.
Incidentally, the last movie was a simulation run at IAPR on CC, and Randy and his group is providing this simulation. Much before the launch, we have some expectations. Now, real observations will validate those. The other thing which I wanted to highlight is, anything comes out of the sun basically has to go to several planets. So we at Lagrange one only seeing some, one directional information. If you really have to have a comprehensive understanding of these huge structure, and as you can see, this huge structure when it comes out at different vantage points, here is Earth, here is Mars. Of course, we are planning sometime to reach Venus as well. And then, if you can go even south of ecliptic and look at the sun from a different vantage point, you expect to get completely different signal. And all these signals have to be corroborated to get a 3D picture of these views. So the future is much more complicated to get a comprehensive understanding, and the amount of volume of data which it will generate, it's impossible to be handled anybody else other than a machine. So this is the era of machine learning, but again, the machines have to be trained. So from sample data, slowly you have to improve the machine. And I'm glad the last talk already just showed you some small samples. We produce terabytes of data per day almost in a solar observation. So here I also wanted to highlight, we are catching up with the rest of the world in terms of space mission. The heliophysics mission, so these are only satellites looking at heliophysics. Now we don't call it sun. It's a solar system and beyond. It's called heliophysics. And from different vantage points, there are so many satellites. And we are entering into the picture slightly later. But we are actually in a very good location for ideal for solar observation, which the Europeans did 20 years back. But we could reach a vantage point and hopefully we'll be able to contribute to this comprehensive understanding of the heliophysics. So this is a particular message to the younger people that don't get fully bogged down that we have our data, but it is going to complement with other observatories, and other observatory data is mostly in the public domain. The NASA has a policy of open data policy. Hopefully, we are also moving into that direction slowly. So this is the message for this. Now I move into my last 10 minutes. Maths for different features of the. So this meeting is feature recognition. So I wanted to just give you a pointer that how much work is there in just our own sun. It is in the archival data and also the data which is going to come now. So you don't have to really worry about this really busy stuff, but I just give you a few names. This is solar wind, which you have heard about, which is the far, outside expansion of the atmosphere. Then you have plumes, interplumes. These are structures. They are funnel-like structures called plumes. Sunspots, of course, we all know here. The solar surface is always showing direct signature that the sun is convective underneath. So there are different kinds of structures. You see granules, you see mesogranules, you see supergranules, and this is a perfect example of convective, simulations as well. And this is magnetoconvection, again, a lot more complicated as well. Spicules are very transient jet-like features. Then there are these huge magnetic structures called flux rope. Eventually, they will erupt. These are called long extended structure on the solar disk. They are called filaments. They become unstable and give rise to again CNEs. These dark regions on the solar disk, they are called coronal hole because their temperature is lower and they seem to be much darker as compared to the surrounding. Now we know that these coronal holes are much more open magnetic field regions, and these open magnetic field regions are the channels for acceleration of the solar wind as well. So it's easy passage to leak out particles as well. These are the CMEs which we have talked about. Of course, there are huge dynamic few millisecond events which are called the flares of different class. So you need to understand why a flare happens, where a flare happens, why there are different classes depending on the magnetic topology and its complexity and so on. So there are a zoo of features on the sun. So if you look at the historical data, you need to identify these features. Thankfully, the modern day the computers are there and the smart young boys and girls are there. I had the privilege of supervising two MTech PhD students. One was from Calcutta University, and they got interested in 100 years of original data, and they did this feature recognition. And now, of course, both of them have good job in US and doing high-level publications as well. So, what are the applications in AI? One is data homogenization and stretching the observation baseline. I will give you example. We are observing in so many different places with certain difference in the instruments and all that. How do you homogenize? How do you compare one data with that other data? The strong calibration is a very, very difficult task. That again, machines can help us. Solar cycle prediction. So I have only so far shown you the sunspot number variation, but then you give a spatial distribution of the sunspot. In the beginning of the solar cycle, the sunspot actually appears in a higher latitude, and then with the progression, it moves into the lower latitude. And this is represented by this butterfly. So popularly, they are known as butterfly diagrams to look at 100 years of spatial distribution of the sunspots. You can reproduce these butterfly diagrams. So we have done that. If you can now study that well, can you predict how the next solar cycle will be? Because the next solar cycle prediction, if it is possible, then of course it will link to the space weather prediction. Because you know at least when the sun is going to be more active and certain things can happen. Solar image classification, feature segmentation, event detection. So these are the different filaments which has been identified in the feature recognition. In fact, in the context of astronomy, of the galaxy classifications are also happening in the same way. There are also inversion problems because you have certain models, certain observations, but you do not have that. Those are not direct observations. You have models, and two models you have to do an inversion. In fact, Solar Orbiter is a mission which is detecting the polarization, the polarization properties of certain spectral lines. But solar orbiter is out of ecliptic plane and it is very, very far away from us, so we don't have much telemetry. So unless the data is processed on board, you'll not be able to do much time. So there is an inversion core which is loaded on the solar orbiter onboard computer, and we are only downloading the data products. So the machine only doing all this inversion, assuming what kind of so that there has been a lot of training in that process as well. So it is all happening. Space weather prediction is going to be completely decided by big models. Homogenization I was just referring to, and again showing examples of the sunspot number data. This has been taken from space. This is again a space, this is again another instrument which has been looking at the sunspots. But the longest observatories at the Mount Wilson, the Wilcox, Kitt Peak, National Solar Observatory, and all that. But then, as I indicated, all these data has been taken from slightly different instruments. So this homogenization is a huge task, and they are having different resolutions as well, different temporal cadence as well. So this is, a huge task for machines. So this is again an example which, again, I'm not an expert any of these, only my students, and I try to learn a little bit from my students how but I only encourage them to move into that direction. So now Shubhamoy, this guy who did his PhD, he's there with Andres now. They published Nature Astronomy last year. So this deep learning kind of thing is also achieving a super resolution. By artificial way, they are achieving more than what the individual instruments are capable of doing. So it looks like very odd. I mean, how can you see something which is not there? By training, so there are, of course, you have to have high resolution images from other instruments, using that as a training thing, and all recognitions and all that will lead to a super resolution kind of cases. Solar cycle prediction. This is a prediction for the next cycle. It has to be verified, of course. We are somewhere here now. Maxima is probably somewhere in next year. So this is what we are just referring to, the spatio-temporal distribution of the sunspot, so-called the butterfly diagram, and this is the forecast. So of course, some forecast happened in the past as well. So people are now comparing and all that. This is the work which was done in the TIFR, and just picked up thing which is also done in India. Sharman's student did this work a couple of years back. We have also looked at scan images. Kudekanal, has looked at the sun, and individuals from 1904 have gone by hand where the sunspot is. There are certain regions called, as I mentioned, filaments. These are actually magnetic neutral lines. Then there are certain regions called plages. They are chromospheric features, about 1,000 kilometers above the surface of the sun. All these features have been manually hand drawn. And in fact, there was a project from Ashish Ghosh was the PI of that center here. I had a fund, and then we scanned all that hand-drawn images, and we do cluster, techniques here. And these results is just recently published in ABJ, and this kind of clustering is done for hand-drawn images. So there are scientific output, and we are comparing the hand-drawn images with the real data also that are taken from some other observatory. You see, the older data, if it is in the photographic rate or films, they get deteriorated. So you have lots of data gaps in those films, where the sun charts are pretty well preserved. They're all taken with the chart papers and so on. So there are enormous amount of sources. Let me put it in the Aditya L1 context. This is the image which you have seen in the Twitter from ISRO. We have multi-wavelength, images in near UV filters, and you see a cluster of these images, and you could, clearly see these features on the sun. You can have plage, as I mentioned, sunspots, filaments. If you have time series, you can identify the transients, prominence eruptions. So unsupervised pattern mining is going to be a huge project for our own data sources. I just show you a comparison. This is the current state of affairs of the Kodaikanal calcium images. Again, calcium 2K line is found in chromosphere, and we have reproduced after lots of processing. This is the state of the art, calcium images taken 1937. So now this is a calcium image from Sood. So we are now looking at continuity. How the old archival data has to be cross-calibrated with the most modern space-based data, and then we have this huge database to do long-term studies for the sun and its impact. The other important element I must point out that magnetic field observation of the sun is only available from late 60s. We don't have last 100 years of magnetic field observation, unfortunately. So you have to look for proxies. So of course, wherever there is a presence of magnetic field, we know that there are certain places which are bright. So here you see the locations where there are bright regions are surrounding the sunspots. So if you can quantitatively know how much is the emission coming, excess emission, you can produce the solar cycle. The irradiance cycle can be, gone. I mean, we could go back to the history and reproduce the irradiance. Similarly, the magnetograms are only available for last 30 years or 40 years. So by doing this, cleaning the data set, we can go back and create the magnetogram. So then we will have a proper, magnetic cycle, estimated or studied. So this is again a butterfly diagram we produced from calcium. This is again Shubham did way back during his PhD. Now we have much more improvement, but I just wanted to highlight that cross calibration of these 100 years of data, understand the solar irradiance using the large set of data, understand the impact of solar irradiance on the Earth's climate. So the point is that there's so much of scope and so many different projects one can look at. It really needs huge, human resources. It's just not possible for few individuals to do. So Aditya is a mission which really demands a lot more people to work on it. And then, as I indicated, generate the magnetic field maps for first century. Real map doesn't exist, so you have to, train the machines to get back to this map. Very briefly, again, the suit payload we mentioned. Now I will talk about the first result from the aspects. This is the X-ray spectrometers looking at the sun as a star. So integrated X-ray flux it is recording. We operated, aspects. Helios. My mistake. Helios. This is a high energy, X-ray spectrometer. We have two X-ray spectrometers. One is called Solix. Other one is called, Helios. And this is a result from Helios, which is showing you the green ones are showing you the X-ray flux. And as I indicated, it's integrated flux in certain energy band. And it is showing comparison with those. These are the best possible NASA satellite, which looks at again a total solar flux. And these spikes indicate the flares. And it appears that we have pretty good temporal coverage. Furthermore, it appears that we have better temporal resolution than ghosts, because as you can see, the ghost fluxes are much more smoother, where we see more spikes. Of course, these fluxes has to be still calibrated. As I indicated, only the doors were open for a few hours, and it essentially helped it. So this is a pre-commissioning phase. So you are seeing data in the even pre-commissioning phase. It's not even commissioned. So that's actually quite exciting, and we are excited about finding this opportunity. And ISRO has really given us a new era. There are a lot more things we can do from AI. Again, very briefly, we can look at the polar region of the sun. As I indicated, we are always looking at the sun most of the time this way. We don't know the polar regions because there is always a huge projection method. So that means either you take the satellite, go out of ecliptic plane and look at this, which NASA is attempting, and ESA is also attempting, but still there is no real satellite with a high degree above the ecliptic. But our machines can do it because as the solar orbiter is slowly increasing its degree above the ecliptic plane, it has some produce some data and all that. So probably we can train the machine to really know about the polar regions of the sun. Better forecast for geomagnetic storms on Earth, as I indicated, that the storms are very, very important for our electrical systems. Estimate the coronal field using photospheric field data. I just very briefly mentioned that the magnetic field of observation has only been possible in the surface of the sun. So these are called by Zeeman effect. We look at the spectral line, and then sometimes the spectropolarimetric signatures. But if you go to the corona, the emission is so weak that we do not have a direct observation of the corona. We have some spectropolarimetric observation. We are the first time doing from space from Aditya mission in our corona graph, but that data will also have lots of noise. The point is always, and I think you also heard about the gravitational wave detection thing, or even the solar, extrasolar planet detection. You are often with a lot of artifacts. So to model the artifacts, what is your signal against the noise? Machine is actually helping a lot. It's just not adding signals, not enough. So that way, it is huge potential in that field as well. There is also far side magnetic map. As I said, we only see the front side. We don't know what is happening in the far side. But there are opportunities with the machine to be able to do that. I think I will slowly, I'm running a little bit out of time. The corona graph, automatically detects the CME. So these CMEs are really these extended structures, as you see here. We have a onboard logic to detect these scenes. So the first time we have put a FPGA cords on board because otherwise the camera takes few frames per second. So we can't store that many images and download them. So we can only store images when it is required. It's like motion sensor cameras what you have from the CCTVs. So so we have lots of scope of the coronagraph in terms of the AI. Automatically detect the CMEs, categorize the CMEs on the different properties, and the space weather focusing models and so on. So for all these, we need lots of last few seconds. Human resources. There is a Aditya support cell at ARIES. We do conduct workshops, and the next workshop is going to be in Kolkata between 6th and 8th of February at IAPR. So please convey this message to the students who are interested to learn more about the Aditya. It was a privilege for me to be there, lifetime experience, and thank you for your attention. I come from this beautiful place called Mukteshwar, and if you are interested to visit our observatory, incidentally, we host the largest two optical telescopes from this part of the globe. I didn't talk about astronomy at all. I only focused on Aditya and related things. I'm sorry for taking a little longer. Thank you for your attention.
Thank you very much, Professor Banerjee, for a wonderful talk. It was perfectly pitched, I would say. I personally learned a lot from your talk. So thank you very much for being here once again. Time for some quick questions, maybe from the audience. Yes, please.
Thank you for your exciting lecture and showing our knowledge page. But I very much interested, particularly for your talk. During the solar burst, the magnetic field actually gets affected, and it generates probably much more cosmic particles. So these cosmic particles naturally will come towards the Earth, but due to the Earth's magnetic field, they cannot enter directly into the Earth. These particles are hazardous to humans. But if we consider the Earth as a magnetic dipole, then along the direction of the magnetic dipole, the particles can enter into the atmosphere, and they will generate the cosmic tree. These cosmic particles will generate the cosmic tree. if I am not wrong, the moving power actually don't do this thing. Now, during the solar burst, this tree also will get affected. And one can check the dissimilarity measure between the two tree structures. So we will form the data set. Is it possible to use this data set to learn a CNN or any other neural network just to predict the sunspot or something like that?
Okay, yeah, and as we pointed out, sometimes the novices ask the most difficult question. Yeah, so there are quite a few different things you have addressed. One is this, the high-energy gamma rays or the cosmic ray detection by the shower is normally done from the high altitude mountains and all that. So in India, also you mentioned Baba started this, and ARIES still continues those kind of programs from, for example, now from Ladakh region. So these are primarily they look at intergalactic cosmic rays, not of solar origin, because the solar origin cosmic rays are more transient in nature, but it does modulate the overall cosmic ray flux, which is coming from many different sources, large example. So the solar cycle has an impact of this overall, cosmic ray flux, because the solar cycle, depending on when the sun is magnetically active, it actually changes the interplanetary magnetic field pattern, and that deflects the intergalactic cosmic rays much more. So we do observe a direct correlation of cosmic ray fluxes with the solar cycle variation, which is much lower in that process. But the solar transients, I'm not sure people have attempted from ground, but it will be possible from space. So we need such detectors in space, because as you said, Earth magnetic field does protect us. So you have to go to really high latitude. Maybe if you go to Alaska and set up a laboratory and all that, you may get better flux. We need more data for doing this. From India, very unlikely to get such fluxes or such transients. But the solar cycle variation we do observe.
One more thing, due to this solar burst, right, some of the radio bands will get affected, and that also affects the community.
Yeah, of course.
So this variability is possible to train a machine.
Yeah, so what you are saying is
Or you can is possible to train it.
So we are looking at four factors. So what is important is to look at the source. Unless you understand the source, you can completely picture out. Because if you are looking into the measurement, you only see and you are assuming that the source is always the same, which is not the case. No two CNs are activity. So if you need to observe 1,000 CNs, it is hard to really cluster them in one group. So people are trying to do that. These animals put it in one basket. If you have such slow CNs, probably you will have such impact. So you keep doing that. So, but there are something in typical models also, because if you want to run full energy models, computers are still not fast enough to give you the complete result. So it's more or less a semi-empirical model, cause and the effect kind of inputs, and they're doing the prediction. The success rate is about 70-80%. Since you asked, in fact, you also have respectable prediction models and all that. So we do need in a national way a big space weather prediction center, which will have capabilities of doing inputs from multiple observations. It's things like our weather forecasting. You see how good the weather forecasting in the West as compared to still us, right? So we need much more sophisticated models and more finer data points. The build points have to be more.
Okay, thank you very much.
Any other questions or comments, maybe? Oh, please.
So you mentioned that we know about the dosage of maybe not lethal, how much it can affect us for it. But you said that we did not kind of quantify that in the case of the spectrum. The spectrum, When so we want the like the ion techniques.
Yeah, we know certain certain can be there is surgeon to ask the question. So we are putting spectrum to be the power spectrum. But again, if we look at the spectrum, where we are energy bands, we need a more complete study. What is happening? So in fact, the other thing is astronomy is really where biologists are down. Astrobiology, I mean, we are talking about understand. We don't understand that much of biology. So, I'm not using, but the biology should say that we need to better quantification. As I indicated, no two scale is the same. We can only use ranges. So, we are going to put very high, velocity scale. Those are they are the most dangerous. But again, the magnetic properties of that theory, the topology of the magnetic cloud is also very important because the north-south direction of our Earth's magnetic field and the alignment of the magnetic field of that is crucial to say what sort of impact would be, whether it will be a geomagnetic storm or not, depends crucially on the direction of the magnet. So there are a lot of data points is still missing. So that's why I'm saying that we do not have a comprehensive quantitative archive to estimate that. But I think this is a need of the hour. The different expertise they talk to each other and get a better communication. What kind of dosage are really harmful and what is not.
One more quick question, maybe we are running out of time. So yeah.
Under the contract, so it's something that going to 0.3 AU. So then my question is just money that makes a difference, or when there are all kinds of technology that we use to put it back.
It's the gravity of the other planets to read. Other thing is the technology in terms of the instrument what we build. So the more closer you go, you are in a much more hazardous thing. Even the temperature is very, very high. So Parker Solar Probe is not looking at the sun, it's actually looking away from the sun. If you remember my movie, it is capturing, so it has a heliospheric measure. It has a lot of particle detectors. So we are trying, Parker is essentially trying to probe the solar wind and all these ejecta which comes its property because it is too close to look at the sun.
Okay, so you already answered my part. The question it was about what's the main science for Parker Solar Probe, and that's about studying the solar wind. It's different from things like sun or thank you.
Sir, I have a question regarding super resolution. When we are testing the images, my question is, are the images weather independent? Because many geostationary satellite images are made. We can check for the training of the super resolution. So are the images specific for L1 or any specific mission, or for training we can take any other geostationary satellite?
That's correct. That's correct. So even geostationary satellites, once you are outside Earth atmosphere, the lower atmospheric things and all that, the distortion in the images are almost negligible. So the resolution gets affected by speed, we call it, from when you have a ground-based observation. So obviously, the solar dynamic observation is the geostationary orbit. Okay. So lower orbit is slightly lower, but that also is good enough for any space observation which provides, clean images, which is only diffraction limited, we call it, because the resolution is dictated by two things. One is your optic, the other one is your detector. And of course, if it is a ground-based observation, your atmosphere. So once you are devoid of atmosphere, your resolutions are dictated by the instrument primarily. So that way, the newer instruments are coming up with a better resolution. So the point is, can you train the machine and make the older images with better resolution? Because better resolution is, bringing up much more details and smaller pieces and all. So that's that kind people are doing. You have longer series than the 94.
I see one hand raising there, so that should be the last question, I think.
Nation, if someone wants to collaborate from the agencies, so who can collaborate and how do they?
Yeah, it's a very good question. So that's why this Tier 1 support cell is there. You can contact us. Of course, you can contact any payload PI. So the payloads have some, some guaranteed time in the beginning. We don't know yet how long. We're trying to minimize that, maybe 6 months or so. If this phase itself you want to get involved, you should contact the principal investigator of each instrument. It is all given in the Aditya. But it takes quite a while to understand how you process this data and all that. So support cell is now doing that training with similar data from other missions. Because some of us have been involved with the space mission for donkey's years now. So my students are, sort of participating in those exercises, and we are going around and conducting these workshops. So these workshops will be the first level entry, and the other detailed thing will be more to directly contact the PIs of the team.
Because we need a lot of domain expertise which helps.
Absolutely. Absolutely. And in this phase, astronomers do realize that handling the data, we have been not really saying AI for last 10 years, but we have been doing some kind of machine learning in our field very long period of time. But in a crude way. I think the time demands now we don't need to do things from scratch, because there's so much sophistication available with the experts. We need to talk to each other and work together. Then it will be much faster and better.
So if there is no more questions, I think let's thank the speaker once again for being here. And okay, so I will just hand it over to the organizers if you have any announcements.
Thank you, Professor Banerjee, for such an enlightening talk. And thank you, Professor Pal, for conducting the session for us. Now I'll request Professor Pal to please felicitate Professor Banerjee with a memento.
Thank you, sir.